Earthquake prediction is no longer impossible. You are about to see strong evidence of that. Why is that news? Because not many years ago, a quote from the Seismological Society of America in San Diego said that seismometers are currently the only source of information used to alert people in the moments before powerful tremors. Now, instead of moments, I'll show days of advance notice. Not just the familiar pre-shocks in time, but also location. This quake is recognized by everyone as a horrendous destructive force. Japan's main island, Honshu, shifted east by more than 2 meters, and the tsunami triggered by the quake produced waves over 40 meters high. Another experience that's fairly well known is the appearance, before a quake happens, of certain changes in behavior that send a hint something is about to happen. We can call those pre-shocks. But here I'll describe something not widely known: quake warnings indicating location. I was able to get that from daily readings in the 4 weeks before March 11, 2011. Investigating other quakes for similar patterns could offer life-saving potential. Here's an image that shows 11 locations surrounding the quake. These locations, spanning hundreds of kilometers, all have monitoring stations that maintain precise positions obtained from repetitive GPS measurements. At first, the information from those recordings couldn't be used for this investigation. A professor from Ohio University corrected the data, and I used his results. To begin analyzing what's going on, I took a method used, believe it or not, in medical imaging. There it's done in 2 dimensions, 2D. Just to make sure that isn't misconstrued, I'll clarify that. There are 3D images, for example, from cone beam scans. But for the medical field, changes in shape are analyzed by combinations of 2D images. A 2-dimensional view of the stations shown in the preceding slide could be presented in the way shown here. Each station, depicted in black, is attached by a weightless connecting arm, depicted in light blue, to the centroid. You can think of the centroid as the CG, center of gravity, when all stations have the same weight. When a quake is brewing, those station locations move in a variety of ways. If they all just move down, for example, the image you see now can change to this. Immediately you realize this is just one of many possibilities. That shift in position could have happened along left and right, or forward and back directions, as well as up or down. So, that 2-dimensional limitation in medical imaging applications cannot handle large distances in all 3 directions. I had to extend the approach to 3D. I'll talk more about 3D soon, but first let's consider another basic type of motion: stretching along a different direction. First, we'll go back to the image you saw before. That's the way it was originally, and now the expansion. As mentioned earlier, expansion is illustrated here in a different direction that we can call X. Not too much more needs to be said about that at this point. Right now is a good time to list that variety of motions mentioned earlier. Here we define the way that's been chosen to describe how things change during the period associated with the quake. The method has a rock-solid foundation in theory, but for this entire description, I'm avoiding the complications. For those interested, some outside references containing more details are cited at the end. Here, it's enough just to state that we locate each monitoring station with standard vector representation, along with standard means of defining the way a vector changes from the earliest day to any other day afterwards. That method uses something we won't talk about much at all. The technical term for it is a coordinate transformation by means of a 4x4 matrix. But again, you won't hear much about that or about the math. To understand everything that follows, all you need is a set of easy-to-understand facts. A 4x4 array has 16 elements. Out of those 16, 15 are independent. Those 15 can be described in terms of 5 effects in each direction. We refer to those directions as X, Y, and Z. The 5 effects are shift in location, rotation, scale, shear, and perspective. Perspective is irrelevant for this investigation. After a little bit about location, shift, and rotation, you'll see more about scaling. Equal scale change in all 3 directions, X, Y, and Z, makes size bigger or smaller. But only non-uniform scale changes affect shape. You saw one example of that in the expansion along the direction I called X. Another example commonly used in 2 dimensions is a square changed to a rectangle of the same area. Shape is changed also by shear, that is, again in 2 dimensions, by pulling on diagonally opposite corners of a rectangle to form a parallelogram. In 3D, 2 non-uniform scale changes plus 3 shears equals 5 total shape variables. Those 5 shape states provide the primary basis for prediction here. So again, for those interested, details are described in the references at the end of this presentation, but right here I skip over the complicated math and just explain the changes we'll consider when this object is seen from different places, from different angles, and so forth. Okay, it's time to show an example of rotation. Here's the original layout again. And now we'll show some rotation. The location shift was down and the expansion was shown across. With that expansion direction called X and the upward direction Z, then the axis of this rotation can be called Y, according to the customary way of expressing motion in all 3 directions. Now we can go back to the subject of position shifts. It won't surprise anyone to hear that the main shifts occur in all 3 directions on the day of the quake. We can call that day number 0. Then the day before that is day number -1. Another day earlier is day number -2, etc., all the way back to 4 weeks before the quake, day number -28. Now you'll see the history of shifts in position from about a month before until a month after the quake. Post-quake shift of Japan's main island, mentioned earlier, was a few meters, but the amounts shown in these graphs are much smaller for 2 reasons. First, they were pre-quake. Second, they represent a whole structure over a span much bigger than that island. That structure is made up of those 11 points. With changes of just centimeters out of hundreds of kilometers, it's easy to understand why the numbers are so small. And with numbers that small, it's easy to understand why high precision is required to get any valid results. I already mentioned that a professor from Ohio University corrected the originally recorded data. Thank God for that, otherwise my results would have been inconclusive. Okay, what captures your attention here is obviously the shift in all 3 directions on the day of the quake. If you look more closely, though, you can also notice smaller jumps on day number -5 and even number -16. By itself, that would be only a minor clue, but I mention it now because it's consistent with much greater effects to be described next. From now on, we'll concentrate on clues that could help anticipate what's ahead. So, we'll just look at what happens before the quake. The rotation you saw earlier was only an example. The actual rotations were much less because, as in the slide that showed the location shifts, they represent the whole big structure spanning hundreds of kilometers. But I noticed a very interesting behavior for the sensitivity to rotation. I made minor changes to the amount, and look at the effect, even on day number -16. more than 2 weeks before the quake, plus bigger effects on day number -1 and much bigger on day number -5. That motivated me to find out more. The effect shown at the right is much less dramatic, but again, it tracks with the timing of exceptional behavior. So far we've demonstrated how advanced warning was possible in time, but nothing has been shown yet about location. That information came from performing a set of steps using all the landmark coordinates for each day. First, after aligning the daily centroid with the earliest day's centroid, that took care of location shifts, and then scaling the daily size to the earliest day's size, and lining up the XYZ axes with the principal directions to take care of rotations, only the shape variables were left. I computed a best estimate for those based on a method that's been well known for decades. Then, using what I just computed, I reconstructed where every landmark would be if those shape variable estimates were exact. Those theoretical locations were generally close to the actual measurements to within a dispersion of about 2 centimeters. Not every landmark moved by large amounts in every direction, but it's well worth noting that some of the migrations easily stood out well above the dispersion. That validates usage of this model based on those 3D shape variables. Now I'll return attention to how that model generally agreed to within about 2 centimeters of the recorded locations. This image shows exceptions to that, especially on day number -16 or -5, and for one particular landmark designated here by a red square. That's actually not a problem with the model. In fact, it's good news because it involves prediction of the location. You will appreciate that much more after seeing the 4-week sequence to be shown next. Earlier I showed sensitivity to the amount of rotation. Now for a 28-slide sequence, I show sensitivity to the direction of rotation. 4 weeks before the quake, and also for a number of days thereafter, you won't see much action. You don't need to bother your head about the numbers or the colors. If you'll just notice changes in this behavior, you can easily become alerted when something is up. Okay, here's the result for 27 days before the quake. Then 26, 25, nothing much happening. 24, 23, 22, 21, 20, 19, 18, 17, 16 days before the quake. That's a conspicuous change in behavior. And it goes back down right away. 15 days before. 14, 13, 12, 11, 10, 9, 8, 7, now watch this, 6, 5, 4, 3, 2, and then one more day before the quake. Okay, now let's return to 5 days before the quake. Remember this? It definitely suggests that something is up. Now consider what information could have existed at that time 5 days in advance. This clearly draws attention to the landmark designated with a red square. As it turned out, that was the one closest to the epicenter. I believe this is enough to encourage looking at data from monitoring stations surrounding epicenters weeks in advance of other quakes. I'll state that formally next. Imagine a quake brewing in the future with an image of the type you just saw made available, along with behavior similar to everything you saw before that in this presentation. That kind of predictive capability might or might not ever become a reality. I can't guarantee behavioral patterns like this being common among other quakes. But I will guarantee that opportunities to notice behavior like this won't become a reality if there's no further investigation. Someone with authority in an institution responsible for public safety should sponsor a project under direction of Professor Frank Van Grass at Ohio University. The monitoring stations already exist, and the demand imposed by sending the data, for example, just one reading each day used here, is insignificant. Letting computers repeatedly run the algorithms for all chosen sites would be simple. So, the research cost would be trivial in comparison with the benefit. How can this opportunity be wasted? As briefly mentioned before, the landmark data originally recorded never would have provided the precise distances between stations, centimeters over hundreds of kilometers, needed for this investigation. The one in charge of correcting the recorded data, thereby making this effort possible, was Ohio University's Professor Frank Van Grass. These sources offer further information. The first is for those who want to pursue the standard 4x4 matrix transformation math I skipped over here. Next after that, you can gain some perspective from the GPS Daily article. It contains that quote from the Seismological Society of America in San Diego about seismometers being the only source of information just moments ahead of the tremors. You can also find authoritative sources not long before that formally stating that earthquake prediction is an unsolved problem, and that perception is still widespread to this day. Some research in recent years has been aimed towards enabling prediction. The investigation I'm describing here, using the data from the third reference, is summarized in the fourth and covered more thoroughly by the last reference, a cover story of Coordinates magazine. In addition to a detailed development, that manuscript includes some tabulations enabling readers to verify some of the numerical results.